Hello, everybody. Welcome to today's lecture. So last time we talked about 6.2. So just to give you a little bit of a refresher of what that was about, we talked about the minimum spanning subgraphs. So that's kind of graphs within graphs that touch every single vertex, and they don't form a circuit. Then we talked about trees, and here I'll go back over to it for a second here. So let me see here. Where did we talk about? Here's the tree, but here's the spanning subgraph. Okay, so we first just talked about a spanning subgraph, and then later we talked about the minimum spanning tree. Okay, so the spanning subgraph was one where you touch all of the vertices basically, and you're not forming a circuit. A tree is a graph that is connected with no circuit. So both of these, you are not touching any circuit. Okay, and then we looked at some properties of trees, which are very useful. And then we looked at the minimum spanning tree. So this is what we were kind of working up to the whole chapter, because this is where we can find like the most efficient path in terms of the cost, whatever the cost might be, like time or distance or actual cost or whatever. So this helps us find the most efficient path. And then we had this algorithm for doing it, which was basically pick the shortest one, now pick the next shortest one, etc. And you just keep doing that, making sure that you're not forming any circuits ever. Okay. So in 6.3, we're going to start talking about what's called an Euler path. And then in 6.4, we're going to start talking about what's called a Hamiltonian path. Okay. So these are two special types of paths that are very important and were studied intensively by their namesakes. Okay. So this section is actually called Euler circuits. Okay. But first, we're going to talk about Euler paths. Okay. So first, a bit about the name Leonhard Euler. Okay, so it looks like Euler, but it's pronounced Euler. Euler. Okay. He was a very prominent mathematician. He lived in the 18th century. He contributed to pretty much every area of math. Any kind of math you're studying, you're going to find this name. If you know the letter E, he was the one to not really discover it, but kind of discover its importance. I mean, he's touched pretty much everything, but not even just math. He did a lot of work in physics. He did a lot of work in music theory, and he did a lot of work in religion as well. So, he was really one of the most prominent scientists in general in the 18th century. It's said that like a good portion of, if you put all of the math work ever done in history, a good portion of it would be purely from Euler. He definitely is known to have contributed the most to math, more than any other mathematician in history. So this is one of the areas he worked on, which was graph theory. He was specifically studying this problem called the seven bridges of, I can't recall the name. It's a city in Prussia. But we're talking about that in the discussion problem this week anyway. So be on the lookout for that, and make sure to read the Wikipedia link that I put in that discussion problem and the discussion problem itself. And then you'll see a little bit more about Euler and a little bit more about the problem that he was working on. Okay. And then we're going to look at a variation of that problem using what we're going to study here today. So essentially what the problem was saying was that there were like 7 bridges in this city. Okay, so there was like a river surrounding the city, and then there were 7 bridges, and there's a picture of it in that Wikipedia link. And he wanted to answer the question, is it possible to take a tour of the city by crossing every bridge only one time. Okay, you want to cross every bridge, but you only want to do it one time. And he ended up showing that that wasn't possible using his theory he developed here with Euler paths. So Euler paths are just that. It's in that context, it would be a path where you go over every bridge exactly one time. In our language, it's going to be a path where you cross every edge exactly one time, and you start and end at different vertices. Okay. So let's just write down the definition of that first. An Euler path is a path. So remember the definition of path from 6.1. That travels through every edge. So every edge of a connected graph. Okay, so this only applies to connected graphs. Once and only once. Okay, so exactly one time. And starts and ends at different vertices. Okay. This last part's a little redundant because a path already has to start and end at different vertices, but just as kind of a reminder, we'll throw it in there. So it's a path that travels. So basically, you want to start at one vertex, end at a different vertex, and go over every edge exactly once. Let's look at a very simple example. If we have A, B, C, okay. So if we have this graph right here, we can easily find an Euler path because all we have to do, we can start at A, travel over this edge, travel over this edge, and then we're done, right? We hit both edges. We only did it one time, and we started and ended at different vertices. Okay, so not too bad. What about this one? So let's do like the same thing. But now we're going to join A and C. Is it possible to make an Euler path here? Well, if we try to, right, we could start at A, go over to B, go over to C, but now we're kind of stuck because we need to hit this other edge, AC, but we can't go back to A, right? Because we need to start and end at different vertices. It doesn't say that we can't touch the same vertex more than once, but we can't end there, which is what we'd be doing here. And here we're going to run into that problem, either way. So there's really nothing we can do here in order to make an Euler path. Okay. So let's look at the example in the book. Whoops. So we have this rectangle with edges at the corners. Vertices at the corners. We have one in the middle and one on each middle actually. So we have A, B, C, D, E, and F. Then we have this edge right here and this edge right here. So all together we have 1, 2, 3, 4, 5, 6, 7, 8 edges. Okay. And then we have 6 vertices. So can we find an Euler path through this? Is it possible to hit every edge while starting and ending at different vertices? Okay, we don't have any methods for doing this yet, so we just kind of got to guess and check. And there's the answer in the book, but let's not look at it and let's try to figure it out ourselves here. Okay. So where should we start? That's our first question. Well, I feel like it would be a good idea to start at F. Okay. So we could go from F up to A. Why did I pick F? Well, F has F is kind of unique here. Well, F and E are both the only two that have an odd number of edges coming out of it, which is something we need to look out for because, if it has an even number of edges, like B or A, for example, that means you can go in, go out, right? If you do that with one with an odd number, you still have one left over, okay? So with A, we could go into A from this direction and then out and into B, and then we go out of B, etc. So it's pretty straightforward, right? With the odd ones, we kind of got to look out for that. Let's see. So now maybe we can go back to F. So we can touch F again, we just can't end there because that's where we started. So right now, what are we at? F, A, B, C, F. Now we could go down to E. And then back to C. Down to D. And then back to E. And there we go. Came up with a path there. So what did we do? We did F, A, B, C, F, E, C, D, E. Okay. That's actually the same one that the book had too. And the book writes it with commas. I just kind of put them all together here, but you can put some commas in there. Okay, so there's probably more than one we could come up with too. I was just looking at the one that kind of came naturally, and how you go about that. There's some tricks to it. Okay. I wasn't necessarily trying to use those tricks, but I was looking out for the same kind of things. Like we want to look out for things that have an odd number of edges coming out of it, for example, like F does. Similarly, it might have been good to start at E because it also has an odd number of edges coming out of it. But let's keep going and then we'll see some of those tricks that we can come up with to look for Euler paths. And before we do that, let's define what an Euler circuit is. That's the name of this chapter, right? Euler circuit. So these are pretty similar. The only difference with an Euler circuit is that you start and end at the same vertex. Okay, so it's pretty much the same as the definition between the difference between a path and a circuit. They're the same thing, except one starts and ends at different vertices, one starts and ends at the same one. Same with an Euler path. An Euler circuit is going to be a circuit where we hit every single edge and then we start and end at the same vertex, right? So definition here. An Euler circuit is an Euler path that starts and ends at the same vertex. Okay. So just like I said, it's it's the same thing. You're just starting and ending at the same vertex. So up here, we would have had to start and end at F. Could we have done that? I don't know. It doesn't look like it, but let's look at some of the theory behind this before we try it out. So also another thing I didn't do up here, now that we're like trying to find a path, oftentimes we might write directional arrows on the filled in part just so we can remember which way we went. I just wrote over here, exactly what the order was, but if we want to really draw it so you can just look at it and see the path, then we might want to start putting directional arrows here. So this is the way that we went. All right. So you either want to put the directional arrows or you want to write the path out here. One or the other. Or both. All right. So let's look at another example. Because I don't think that there is an Euler circuit in here, but we'll come back to it after the check. But let's look at this example from the book, which is designed to have one. Okay, so we have an edge here. A vertex here. We have one at every corner, and then the ones in the middle. Okay. So how could we find an Euler circuit here? So we want to start and end at the same vertex. Okay. So again, I don't really know where we're supposed to start. I think maybe it would be easiest to start at like E or F because they have the most edges coming out of them. So we have a lot of different options of ways to go. So let's just try that, see how it goes. Right, so we're starting at E. And then I guess we'll go up to A, over to B. Like right now, I'm just guessing and hoping it works. In a minute, we're going to have some theories that'll tell us exactly how to do it. And then we can go this way and then go back. Okay, so now we've hit 3 out of the 4 on E, which is what we want because we need to have one left over so that we can come back into E at the end. Because remember, we started at E, so that means we have to end at E also. Because we're making a circuit. So now we just pretty much follow the path. Okay. So it worked. And there's probably going to be several ways that you could do this, several different places you could start at. So we did E to A to B to F, back to E, back to F, to D, to C, and then back to E. So the first and last letter have to be the same when we're making the circuit here. It looks like the book used the exact same one, so I guess that's the one that comes the most natural. But you could just as easily have started at F, I'm sure, and I'm sure there's other places you could have started to. I mean, you could pretty much just like you could take this E off and then put an A at the end here, and then that's the circuit, right? You could just kind of like move it over one notch because this is a circuit, so it's looping back around on itself, so it's actually a lot easier to tweak it. You could just take the first letter off and then add that letter to the end, and then you would have the same thing. You'd start at A and do everything exactly the same, except then at the end you'd come back to A. And I mean, you could do the same thing with B, right? Just start at B, go this way, back to B. So, I mean, you could just move this one around and make any of them the starting position and go the same way at the end since it's looping back on itself anyway. So let's look at these theorems here, which are called Euler's theorems. Okay. And honestly, I don't know for sure, but I'm gonna guess if you Google Euler's theorems, you're gonna get a lot of different things coming up because, like I said, he contributed a lot to mathematics. So there's probably a lot of things called Euler's theorems, but I don't know that 100%. So these would probably be called like Euler's theorems of graph theory or something like that to specify which ones. So number one, and there's three of them. If a graph has any vertices of odd degree, okay, remember degree, the degree of a vertex is how many edges it has connected to it. Okay. Then it cannot have an Euler circuit. Okay. So this is very useful. If we're saying, okay, can we make an Euler circuit out of this? All we have to do is look at the vertices, see if any of them have an odd number of edges coming out of it. And if they do, we immediately say, no, we can't. If we go back up to this one, A has degree 2, right? It has this edge and this edge connected to it. So do B, C, and D. E has degree 4. It has this edge, this edge, this edge, and this edge. So, and same with F, it has degree 4. So nothing has degree 3 here. Let's go back up to this one. So this is where our problem comes in. F has degree 3 and E has degree 3. So we are not able to make an Euler circuit out of this. It would be a good idea to try and see why it fails. But you'll notice pretty quickly why, if it has an odd degree, there's going to be no way for you to complete a circuit. It will especially be obvious if you have any edge that only has 1 degree, a degree of 1. Just, for an example here. Think about something like this, right? These three over here, well, this one has degree 2, this one has degree 2, this one, sorry, you can't see what I'm doing. This one has degree 1. This one has degree 2. This one has degree 2. This one has degree 3. This one has degree 1. We can immediately see the degree 1 is going to be a problem for making a circuit because once we go over to this one, there's no way to get back out of it because we can only use every edge one time. So once we go here, we can't get out of it. And if we start here, we couldn't get back to it. So that would be a problem. And anything with odd degree pretty much is going to have that same problem because once we use 1 to go in and 1 to go out, then like if it has 3, for example, on this one, there's no way to utilize that third one. You have to go in and out of it, right? Every time you go into it, you have to go out of it in order to make a circuit where it loops back on itself. So you need an in and an out. And if you have to do it twice, that's fine, but you need an in and an out again. So we're always going to need an even number. So the natural question now should be, okay, if all my vertices have even degree, am I guaranteed an Euler circuit? Well, let's look at the next part of this. So this is still part of number 1 here. If a graph is connected, okay, we always have to have it connected. If it's not connected, we can't even really talk about this. If every graph is connected and every vertex has an even degree, then it has at least one Euler circuit. Okay. Usually more. So the answer to that last one is yes, as long as it's connected. But if it's not connected, we're not really talking about this anyway. So if you have every vertex with an even degree, and it's connected, then there will be at least one Euler circuit. Now, I was talking before about how you could just kind of like switch the order here. Like you could do the same circuit, but you could start at A and end at A. That's still counted as the same circuit in this context. It's not counted as a new circuit because when you draw it out, it's going to look exactly the same. When it says usually more, it's talking about a completely different circuit where you're going in completely different directions. Like maybe you start at F and you don't go this way, but you go this way or something like that. Like you could completely reverse the directions. Even that's really counted as the same circuit, I believe. So it's talking about like when it says usually more, it means usually there will be more that are completely different. Maybe it's in a completely different order here. Like B doesn't follow A. Or that's probably a bad example because it kind of has to. But just changing the order isn't what it's talking about. You can always just change the order. It's just that that's counted as the same circuit. So this is theorem 1 altogether. If there are any vertices of odd degree, there's no Euler circuit. And if it's connected and they all have even degree, then there will be at least one Euler circuit. So this will be really useful for the discussion problem, where I ask you if it's possible to find an Euler circuit. All you need to do is look at the degrees of the vertices. Let's look at Euler's theorem number 2. This is about Euler's paths now. So remember, the paths, the same thing, it just starts and ends at different vertices. If a graph has more than 2 vertices of odd degree, then it cannot have an Euler path. Okay. So for circuits, once you have any vertices of odd degree, it's impossible to have the circuit. But for an Euler path, it still is possible. You just can't have more than 2. Now, this isn't to say so far that if we have 0, 1, or 2, it's guaranteed. The next part of the theorem says if a graph is connected, so again, it's always just got to be connected. If it's not connected, we can't even really talk about this. And has exactly two vertices of odd degree, then it has at least one Euler path. Okay, usually more. So this is it's not exactly the opposite statement, right? Because we're saying if it has exactly 2 vertices of odd degree, then it has at least one Euler path. So we're not saying anything about if it has 0 or 1 vertices of odd degree. We would still have to kind of figure that out. It goes on to say, I didn't write it here, but it goes on to say that if it has 2 vertices of odd degree, the Euler path that it has to start at one of them and end at the other one. Okay. Which should make sense if you draw it out. It's going to, because like I said, if you have ones of odd degree, you don't have an equal number of ins and outs. So the 2 vertices of odd degrees, one of them is going to be an out, one of them is going to be an in, right? So we'll look at some examples of all of these in a minute. Let's write down theorem number 3 first. The sum of the degrees of all the vertices of a graph the sum of the degrees of all the vertices of a graph equals twice the number of edges. And therefore must be an even number. We'll think about what this says in 1 second here. Therefore, the number of vertices of odd degree must be even. This is a little weird, right? Let's think about what this is saying. The sum of the degrees of all the vertices of a graph equals twice the number of edges. Okay. Therefore, it must be an even number. Why is that the case? We'll think about that. Therefore, the number of vertices of odd degree must be even. Okay. There's a kind of a lot going on here. So we have our argument. We have our first premise and second premise and our conclusion. So first we need to understand what the premises are saying. Then we need to understand the conclusion. Give me 1 second. All right. So let's take a look at this definition here. So let's first verify that the sum of the degrees of all the vertices of a graph equals twice the number of edges. Okay. Let's go look at one of our examples and just make sure that it's always true. Right. So let me write it in red here. So the number of edges, well, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. And now we want to look at the sum of the degrees of every vertex. Okay. So let's look at what the degrees are. The degree of A is 2 because there's 2 edges connected to it. The degree of B is 2. The degree of F is 4. the degree of D is 2. Whoops. The degree of C is 2, and the degree of E is 4. Okay. So what's the total here? We got 2 plus 2 is 4, plus 4 is 8, plus 2 is 10, plus 2 is 12, plus 4 is 16. So there you go. So it seems to check out. Proving this would probably be a little more difficult. We can check our examples like I just did here. Coming up with a simple explanation of to why this is true. It's probably not gonna happen. I mean, I guess if we just think about like for every edge we have, that's adding a degree to 2 different vertices, unless there's a loop, right? So for this edge AB, it's adding a degree into A and a degree into B, right? So that's really all that's going on here. For every edge here, it's connecting to B and connecting to F. So it makes sense that there would be twice the amount of degrees as the number of edges. Okay. Loops would throw it off a little bit. I think I might have said before that loops count as 1 for the degree. So I'm not sure how that fits in here. It could be possible that we're counting loops as 2, but I don't think the loops will really come up anyway. If they do, we'll go deeper into it, but for now, we'll just keep that in the back of our minds as something to look out for. I might have to do a little more research on that and get back to you guys. Okay, so we verified that the sum of the degrees of all the vertices of a graph equals twice the number of edges. So let's look at the parentheses now. Therefore, it must be an even number. So all this is really saying is that 2 times anything must be an even number. Okay, and that's true because by definition, an even number is something that's divisible by 2. If you take 2 and multiply it by any number, say like k, it doesn't really matter what the number is. It doesn't matter what k is, this is going to be divisible by 2 because you have this 2 right here. Right, so 2 times anything will be an even number. And you can try that out, right? 2 times 3 is 6, which is even. 2 times 11 is 22. 2 times 14 is 28. So it works out. So we verified the first 2 parts of this. Therefore, the number of vertices of odd degree must be even. Okay. So let's think about what this is saying. This is essentially saying, okay, if we go back up to this, think about all the numbers we added up. These are all the degrees, right? So here there were 0 vertices of odd degree. So it worked out. What this is essentially saying is that if we add up all of the degrees, like let's say we have D1 for the degrees of the first vertex, plus D2, plus D3, plus D4, however many of them, then we should get an even number, which is like 2 times a number by definition of what an even number is. Okay. Well, why is this true? We already know this is true. Why is it true that the ones of odd degree must be even? Well, let's assume that it's not true. Let's assume, for example, that we have 3 vertices of odd degree. So an odd number would look something like this. Okay. So this is how we write odd numbers. This would be an even number. An even number is something times 2. So an odd number would be something times 2 plus 1, right? It's essentially the number after an even number. So any odd number you want can be written like this. For example, if you let a be 1, then this number would be 3. If you let a be 0, this number would be 1. So we can write any odd number in this way. If this is a little confusing, it's okay. You know, I'm just kind of trying to show why this is true. We really just need to know how to use it more than why it's true. But okay, let's say that there's there's 3 vertices of odd degree. Okay. And you could do the same argument with any odd number. I'm just choosing 3 because it's the smallest one besides 1. Then when we add these together, we have 2 times a plus b plus c plus 3. Right. I'm just factoring the 2 out from the a and the b and the c since they all have 2 in common. This number right here, this part of it, the 2 times a plus b plus c, this is always going to be even no matter what a, b, and c are because we're multiplying it by 2, so that's always going to make it even. When we add 3 to it, this is an even number plus an odd number, which is going to give us an odd number. Okay. So when we have a odd number of vertices of odd degree, we get an odd total. This says we must get an even total. So the problem here was the fact that the number of vertices of odd degree was odd. So the number of vertices of odd degree at the end of the day needs to be even. Otherwise, this is not going to add up to an even number. If it was even, like if it was only 2, then what we get here is 2 times a plus b plus 2. So we have 2 times the number, and then we're just adding 2 to it. So an even number plus another even number, we end up getting an even number. Okay. So this is just telling us basically what to expect. We should always have a even number of vertices with odd degree. So this will help us answer the question about the loop actually and how they're classified. So I'm thinking I misspoke in the last video now. Let's verify. Okay. If we have something like this, where there's a loop, and then there is a, we just have these 2 vertices. If we count the loop as only one edge, then the degree here would be 2, and the degree here would be 1. Now we have an odd number of ones with odd degree, right? We have 1 that has an odd degree. So we just show that this can't be possible. So therefore, the loop must be counted as 2. Okay. So I definitely made a mistake before when I said that the loop was only counted as 1. I don't think the book ever mentions which way is counted. So that was just what I thought. So the loop must be counted as twice. Twice. Once when it goes out, once when it comes back in. Okay. So, and that's fine that I said it wrong. This is kind of how math goes. Okay. We think something and it seems like it's true. Then we're presented with new information and we can think about, okay, well, was that really true? Can we prove it either way? So we proved that this statement must be true. Therefore, the statement earlier, which I wasn't sure about, that must have been false. So here's how we can correct it. Okay. And that's how math is. We learn from making the mistakes. I think we learn the most from making the mistakes. I learn the most from problems that I spend like hours on trying to figure out and just doing completely wrong things because you learn a lot from those wrong things. So that's all to say, this, when we have a loop, it's counted twice in the degree. Okay. Okay, this is actually going longer than I thought. I thought we were going to get through 6.4 also, but it's going to go pretty long if we do that. So we'll probably just finish 6.3 and talk about 6.4 next time. So let's talk about the last thing here in 6.3. How do we find the Euler circuit? All right, we have all these theorems about whether or not there will be an Euler circuit. Now, in order to use these, we're mostly going to focus on the first two. The first one is about when do you have an Euler circuit. The second one's about when do you have an Euler path. The third one is a nice statement, but it's not very useful for us, right? This is kind of just confirming that it's kind of just confirming information that will always already be given to us, right? The first two are actually useful because if we want to find an Euler circuit or a path, we can use them. The third one, it's not going to be super useful for us. So in terms of finding the Euler circuits, assuming, so we use, for the circuits in particular, we use the first theorem to determine is there going to be an Euler circuit, namely, are there any vertices of odd degree? And if it's connected and they all have even degree, we know there's going to be an Euler circuit, but how do we find it? Okay, so finding an Euler circuit. So one is basically confirm theorem one, which is be sure every vertex in the network has an even degree. Okay, so confirm theorem one holds true, and that we should even bother pressing forward. Two, begin the Euler circuit at any vertex in the network. Okay. So this is different from the Euler path, because with the Euler path, if we have vertices of odd degree, we can still have an Euler path, but we need to start and end at those vertices. So we only have two choices. With the Euler circuit, we can start at any vertex. Step 3, as you choose edges, never use an edge that is the only connection to a part of the network that you have not already visited. Okay, this one's a bit longer, so let's think about it. So as you choose edges, never use an edge that is the only connection to a part of the network that you have not already visited. So if you haven't been there and this edge that you're thinking about is the only way to get there, don't use it. Okay, let's go back up and think about what this would mean in this one here. This was our only circuit. So I started at E, right? And then I go to A, then I went to B, then I went to F. Now I went back to E. I don't know if we really ever run into this problem in this one, actually, because I think we can always go any direction. EABF. Yeah, I think because of this loop here in the middle, we'd never run into this problem anyway. So there's a better example in the book, which we can look at after I do this, after I put the last step down. But essentially, so if you're going through the vertex and through the graph, and you're deciding which edge you're going to go down, right? You don't want to use one if it's the only way to get to a certain part of the network that you haven't already been. Okay. So that's the goal. The last one's not even really anything. It's just saying to label the edges. So label the edges you've traveled down. Label the edges you've traveled, and I'm just going to sum this up. Continue until finished. Okay. So that's all it's saying. Just label the edges you've traveled and continue until finished. Okay, let's look at one more example for today, so we can see how this is used. Let's use purple here. So this is the example from the book here. A, B, C, E, D, and F. Okay. And now we have lots of edges. We have a couple going this way. Okay, and I think, oh, I missed one from E to F. Okay. So we want to find an Euler circuit out of this graph. So step one, check that every vertex has an even degree. Okay. So let's go with degree, vertex. Make a little chart here. So we have A, B, C, D, E, and F. Okay, A, the degree of A, we have 1, 2, 3, 4. For B, we have 1, 2, 3, 4. C, 1, 2, 3, 4. D, 1, 2, 3, 4. E, 1, 2, 3, 4, 5, 6. F, 1, 2, 3, 4. Okay, so far so good. All right, every vertex has an even degree. Now notice there's a lot of edges here. So our circuit's going to be pretty big. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I can't remember which ones I already counted, but there's a lot. 12, probably more than 12. I think I missed some. Begin at any vertex in the network. Okay. Where should we start? I don't know. Let's start with A. It's the first letter. I really don't know where to start. I'm not looking at the book solution. I like using green for this. So let's start at A. Okay. And we need to end up back at A eventually. So where should we go? Well, all we have to think about here is step 3. As we choose edges, never use an edge that is the only connection to a part of the network that you haven't already visited. We haven't visited anything, so it doesn't really matter. none of these are the only connection to a part of the graph because there's lots of connection to all these parts, right? They all have pretty high degrees. So let's head over to B. And then maybe we could just go down to C this way. And then we could go back up to B. I'm just doing this randomly. I don't really know what's going to work. And along the way, we want to label them so that we remember. Or you could write it down here too. Right, B, C, B. Then maybe we could go over to E. And then we go over to C. Okay. And now we go to D. So notice I'm not really getting hung up on that step 3. I'm just kind of trying things and making sure that they work. And I think that's really how you're going to end up doing most of these problems is just trial and error. Just try to go to somewhere if you want to and see if it works. If it doesn't, back up and try something else. Okay. D. Then we can go to E. Now remember we have to get the A eventually. Back to A eventually. So let's go over to F. So I don't want to use up my ones on A too soon. Then we'll go to D. And then we'll go back to F. Now we'll go to A. And then finally we go to E. And then back to A. Okay. So there we go. So we just didn't really run into any roadblocks. There were lots of ways we could go here. The book has a completely different one actually. The book goes from A to E to A, etc. So it still starts at A, but it goes to E first instead of to B first. So take a look at that one. I think it's actually the same circuit. Yeah, it's the same circuit. It's just moving the AEA part to the front. And then everything else follows, I think exactly the same. Yeah. So the book, it actually does have the same circuit. It just started in a different place, but it's the same direction. But there should be more than just this one. Like the theorem said, usually there's going to be more. It's not guaranteed, but it's probable. Okay. All right. So that's it for this chapter. In the next chapter, in 6.4, we're going to look at what's called a Hamiltonian circuit. Yeah, it's called a Hamiltonian circuit. Like I thought, it says a Hamilton circuit and Hamilton path after. I'll have to see which one it really is because the book uses both. But Hamiltonian circuits, Hamilton circuits, whatever it's called. And Hamilton paths. This is going to be similar, except with an Euler path and Euler circuits, we're using every edge exactly once. With the Hamilton circuits and path, we're using every vertex exactly once. Notice here, we used every vertex many times, right? A shows up 3 times, E shows up 3 times. So we're using them a lot. With the Hamilton ones, we only want to use them one time. Okay, so it's going to be very different. So thanks for watching today. We'll do that one, on the next class. The assignment for this week will be up soon. And yeah, let me know if you have any questions. And thanks for watching.